Hey everybody, hope you guys had a good weekend. I am out with a power outage today as you guys are watching this. So, everything's up on Google Classroom. Hopefully you've already done the engagement survey and are on to step 2 here, which is to watch the kind of lesson part of the day. All right, so our lesson today, our topics are going to be Introduction to Momentum and Impulse. And basically, momentum is when two objects are pushing off of each other during a collision. You guys already answered what you thought collision might be in like everyday language. In physics, it's a much broader term that means any objects pushing off of each other or separating or coming together, colliding. So it doesn't have to mean like a car crash or something. So we're going to do this in one dimension primarily. You guys know that when solving in 2 dimensions, you really just do the one-dimensional thing twice. Not a big deal. What this is really useful for as a type of physics is tracking events over very, very short time spans and getting some possibly huge force and acceleration numbers. So like if you drop your cell phone on the floor, the time of impact for that can be, like in the millisecond range. It could be like 0.05 seconds or 0.01 seconds. And so it's hard to use conventional motion math like we've learned in Unit 1A, or to think about like kind of more static forces like we did in Unit 1B. This will be very short time spans, very large forces and accelerations, a great way to model through that without getting stuck on stuff. And it does involve our velocity, mass, and time relationships as well as force. So that's the goal for today. Is by the end of today, you guys will know what these terms mean. You'll be starting to think about how to calculate them and how to relate them into some bigger picture ideas. So getting started, we got momentum is, well, let's back up actually. Inertia was the property of mass that makes it hard to accelerate. So like a planet has a lot of mass, it is hard to change the speed of a planet. Momentum goes kind of a little bit further than that idea. That's when the object is already moving, and if it were to collide with something, it's got a lot of oomph, like it'll definitely be able to affect the other object a lot. So momentum isn't just the mass anymore, it's the mass times velocity. And that's our first equation right here, which is like, how much stuff do you have? How fast is it going? The multiple of those is like how much it could affect another object if it actually hits and collides with it. So for example, freight train, high mass, if it's moving at a high speed, don't get in the way of it. It has too much momentum for you to handle, and the momentum transfer to you would be bad. Now, that thing that looks like a lowercase p, by the way, that's actually the Greek letter rho, whatever. You can just draw it in as a lowercase p. So p is going to be our variable for momentum. And again, it's mass times velocity. Now let's say you did have something like a heavy shopping cart and you were getting towards your car and you wanted to slow it down and you wanted to decrease the momentum of it. How would you do that? Well, the obvious answer is you would push on it with some force for a certain time period. Like you can't do that instantly. You can do it in a very short period of time if you use a ton of force. Basically, if you want to change something's momentum, then push on it for a little while. That's what this next equation says, and this is called impulse. So impulse is when a momentum changes. And that's exactly what that triangle right there means. That's called delta, another Greek symbol. When you put delta in front of some other variable, instead of just saying the variable, you say the change in momentum. So that's what that delta means. You can also just say delta rho or delta p. So that triangle means that the momentum is changing. And our name for that is impulse. I want you guys to think of those as synonyms. Impulse is the change in momentum. Change in momentum is impulse. They're interchangeable words. By the way, if you were changing something's momentum, probably what you're changing is its velocity. So hopefully the second equation is like no duh. If the momentum changes, you must be changing its speed. A third no duh equation is if the momentum has changed, then there is now a difference from before the initial momentum and after the final momentum. So if your initial and final momentum don't match up anymore and they're different somehow, then the momentum has changed. So these equations, these latter two, I hope are like basically obvious. Now, we're going to work with this stuff one object at a time. We're just going to like worry about one thing's momentum changing. We're also going to think about the big picture. And in physics, that's called the system. The system means when you're tracking multiple objects together. And what gets really interesting is when you do this, momentum is a conserved property. What that means is that momentum is like a physical inherent attribute of the universe, and it can't appear or disappear. It can only be transferred around. So like if you saw a train slow down, you would need to realize that that momentum is not disappearing, it's going somewhere. It might be going into objects as big as the Earth, And because the Earth has such a big mass, you're not going to notice a velocity change for the Earth. But you could actually go in and calculate by how much the Earth's velocity changed. It'd be like an incredibly small number. On a more like day-to-day basis though, like if you see the white pool ball stop all of a sudden after having moved, what you probably need to realize is that there was some other pool ball in the way that got the momentum transfer from it and bounced off and is now moving instead. That's a great example of a momentum exchange. Momentum isn't just destroyed, it's not just created, it's only exchanged. And that means that if you can keep track of the total momentum in a system means all the relevant objects in physics, then you can actually use this as a problem-solving strategy. One other thing we're going to do is we're going to differentiate between elastic and inelastic collisions, and that was one of your warm-up questions too. Elastic means that the object stays separate from before and after the collision. So basically that they're bouncing off each other. And in fact, in physics, it means that they're bouncing perfectly. And we'll cover this more when we get into energy. Truly elastic collisions are unrealistic, but many collisions are close enough that the math is fine. We can model them as fully elastic. Similarly, inelastic is the opposite. That is when there were two separate objects, either before or after the collision, and on the other side of the collision, they were completely, totally stuck together. So like, let me give you an example of an elastic. If I drop a well-inflated basketball, ideally it would bounce right back up to the same height I dropped it from. And if it did that, it would be fully elastic. And in reality, it gets most of the way there. For inelastic, let's say I drop an egg. It does not bounce at all. It splats and connects with the floor. So elastic means bounce perfectly. Inelastic means stick perfectly. And then in real life, collisions are kind of somewhere in between these two, but you can usually model them as one or the other in order to keep things simple. There's a quick definition of terms. Let's continue recapping these terms here. Okay, so we got variables, new variables. We got rho, which technically, Greek letter, whatever, call it lowercase p if you want to. That stands for momentum. Anytime you put the triangle symbol in front of it, that means the change in, and in this case, the change in momentum is also called impulse. Now, if we look at momentum, it is mass times velocity, right? We got a mass, that's measured in kilograms. We got a velocity, that's measured in meters per second. So the unit label for momentum is kilogram meters per second. Meanwhile, for impulse, the main equation we're going to use is force times time. Force is measured in newtons, time is measured in seconds. So the unit label is Newton seconds, just the multiple of those two things. And one thing you might be wondering is, how come if they're really the same thing, are they getting two different sets of unit labels? And the answer is they're not. So starting out, force is mass times acceleration. Newton's second law, equation you're well familiar with by now. Mass is measured in kilograms. Acceleration is measured in meters per second squared. So a Newton is a kilogram meter per second squared. A Newton is a compound unit, meaning it's a way of simplifying multiple units together and bundling them into just one thing to make it easier to talk about. If I break this back out, if I have a Newton second, which is the measurement for impulse, then what I really have is a kilogram meter per second squared times seconds. What happens is a second's in the numerator and the denominator cancels off. And what are we left with? A kilogram meter per second, which is the units for momentum. So keep in mind, a kilogram meter per second and a Newton second, they mean the same thing. They're interchangeable. We just typically associate the former with momentum and the latter with impulse, strictly because of convenience. They're not actually different at all. All right. We got these four equations here. Probably take a second to jot those down on some scratch paper because they're going to be very helpful in the concept builders, which I'm going to give you guys a tour of next before I get back to some bigger picture problem solving ideas. Take just a sec and jot those down. Equation for momentum, the primary equation for impulse, and then two other ways of expressing impulse. Alrighty, hopefully you've jotted those down. We're going to take a look at some concept builders now. Here comes the first of the two. Oh, actually, you know what? This is the second of the two. Let me get you the other one. Impulse, momentum change. We're going to do that first. Definitely do this in this order. Okay, so starting out, we have an object before a collision, that very same object after the collision. We're not really worried about what's happening to the other objects involved. We're just tracking one object. So we're not worried about conservation yet. We're just trying to find out what was the impulse that caused a momentum change. So it says right up here, the impulse beforehand, this is on easy level now, was 8. And the impulse afterwards was 18. By how much are they different? Oh, from before to after, it looks like it went up by 10. So what I need to do next is find an impulse of 10. Now, impulse is a force times a time. So that one would provide plus 10 Newton seconds of impulse. And change that from 8 up to 18. Easy. All right, in this one, our momentum beforehand was 5. Our momentum afterwards was 25. By how much did it change? Plus 20. Looking down here, is this the right answer? No, that would be plus 100 Newton seconds. This is the answer I want right there. The multiple of force times time gets me impulse. Alrighty, here we need to go from 8 up to 24. We need to add 16 Newton seconds of impulse. Oh look, they're not giving us forces and times. They're just straight up giving us the impulse change. That's even easier. So I want you guys, whenever you're doing this, to watch what variables and unit labels are on here, so you can figure out which part of the equation to think this through with. In this case, we just need to add 16 to 8 to end up with 24. Done. All right, I'm going to show you guys a little bit harder levels. Go to the intermediate level next. All right, now notice that this says velocity, not momentum. So what I need to know is the total momentum beforehand is the mass times the velocity. So P equals mv, or rho equals mv. So that's 3 times 4 is 12, 3 times 10 is 30. Okay, 12 up to 30 is a difference of 18. There we go. Impulse needs to be plus 18 to get that to work. All right, here we got a momentum of, see, mass times velocity. Oh, okay, 24. And here is 60. And those are different by plus 36. Here's plus 36. A force times the time makes impulse. So basically, you guys are just working with knowing that momentum is mass times velocity, and that impulse, the change in momentum, is either force times time, or you could think about the difference between the impulse before and after, or you can think about a single mass changing its velocity by some amount. If you guys are thinking through the relationships of those 4 equations there, oh, they're right on the screen. What am I doing? Then you're good to go for this concept builder. That's all it's asking. Let's look at the last menu. They try really hard to throw you for a loop, but don't be fooled. Okay, what they're doing is breaking this up into a 2-stage collision. So you need to find a combination of 2 impulses that provide the overall correct amount. Okay, they're also going to occasionally switch some arrows on you. See how that's a backwards arrow? This velocity counts as -9, not +9. So just keep an eye out for some details here. All right, so beforehand, we got a momentum of positive 60 kilogram meters per second. Okay, plus 60 before. Afterwards, it's -90. Think about this on a number line if you need to, if that's a little tricky for you to visualize. Okay, we had plus 60. Here's 30, here's 0, here's -30, -90, -120. We ended up at -90, right? How much did we change by from here to here? We dropped our momentum by 150 kilogram meters per second. And what they're saying is we needed to do this in 2 stages. So looking back at this one more time now, All right, I need everything down here to add up to negative 150. So here's negative 180 plus 30. I'm just finding a combination of two choices that together make negative 150. All right, I know that's a little more math intensive to add that extra step. Let's do another one here. Here we're going from velocity, mass. Okay, here we're going from 60 up to 96. That's a difference of, or an impulse of, a change in momentum of, plus 36. So now I need to find a combination of two things that gets me plus 36. So here's 48 minus 12. And you can take your time doing that math if you need to. Just find the combination that adds up to the correct overall total value. So yeah, this one might be a little trickier, but don't be fooled by doing it in two steps. You just need the right combo. All right, now what we're going to do is jump back into the lesson for a sec. And we're going to talk about using the law of conservation of momentum to think through this in a little bit bigger and broader context. So here's a typical one-dimensional law of conservation momentum word problem. As you're reading through that intro there, how many objects are we dealing with? Two objects. We have a dog and a mailman. Okay, let's see. What I'm going to do is start to set up a word problem where we're tracking the momentum of each object before the collision, and we're tracking the momentum of each object after the collision. In question 2, I'm also seeing the word inelastic, which means the two objects are going to be stuck together. And I'll show you real quick what the difference between elastic and inelastic looks like. So let's go to DocuCam. All right, so I'm going to make object 1 the dog, and I'm going to write m1v1. That multiple is the momentum of the first object. And I'm going to add that to m2v2. That's the mailman now. And the total of those is the total momentum in the system. System means all the objects that are relevant that you're tracking before they collide. And that total has to add up to the same amount after they collide. This is a law of conservation of momentum statement. The total momentum before the collision has to stay the same as the total amount after the collision. What the collision is doing is it might be redistributing where that momentum is, but the momentum can't just appear or disappear. The total amount stays constant. This was a really big idea I just wrote down. The two objects whose momentum we're tracking beforehand have to still have the same total after they've collided. Okay, I'm going to plug in some stuff. I see the dog has a mass of 10 and is running at a velocity of 5. The mailman has a mass of 70 and is running at walking casually in the opposite direction at a velocity of 1. So now what I can do is multiply that out. 50 minus 70. Okay, I get negative 20 kilogram meters per second of momentum for the system as a whole. System means combined everything you're tracking, all the objects that are relevant. And we've just answered question 1. Total momentum in the system is negative 20 kilogram meters per second. The other thing we can do is we've got this equal sign over here. Now, if these two objects are stuck together, like if it's inelastic, that's telling you that like the dog jumped on or bit the mailman's leg or something, those two objects are now combined into one bigger object. What you can do, and this is only for, right, like this is a great way to write an elastic collision. See the two objects beforehand are separate, and the two objects afterwards are separate. What I can do if I combine them is I can combine their masses into one bigger item, and I can have them both going the same speed now. This isn't like a separate speed for object 1 and a separate speed for object 2, which shows that they're moving independently of each other. Instead, now the combined object is going at the same speed. Okay, so this is a way to reformat this equation when you know that on that side of the collision, whether it's before or after, things were inelastic. They stuck together. This is a very important format to think about. All right, so anyway, I got a combined mass of 10 and 70 is 80 times some unknown velocity. So negative 20 equals 80 times v. I'm going to divide both sides by 80, and I'm going to get negative a quarter meter per second is the velocity. Let's make a cartoon of this. So like the little dog was running pretty fast. Oops, that looks more like a cat, whatever. And then big old mailman is walking slowly the other direction. That's before they collide. After they collide, the mailman is continuing, like the mailman's direction 1, right? Like they had more momentum than the dog did. That was bigger number. The mailman's direction 1. But because they're combined now, this person has had to slow down quite a bit, and this dog has not just slowed down, but actually reversed a smidge. So after the collision, the combined speed is in the mailman's direction, but at a very slow rate. All right, and so what we can say about that is, because the mailman had so much more mass, when the impulse was applied to them, their velocity only changed by 3/4 of a meter per second. Whereas the dog's velocity, because of their small mass, the impulse provided a bigger velocity change of 5¼ meters per second. So the lower mass object has a higher change in velocity as a result of the same impulse in both directions. And that, I think, is exactly what you guys would expect. Now, which one experienced a bigger force during the collision? No. Newton's third law says force from object A to B is going to be equal and opposite to the force from object B to A. Equal and opposite forces. So 4 is a trick question again, just reinforcing that. And that's actually part of what provides the same impulse to both objects. So this was your first like full-blown, one-dimensional, two-object momentum conservation problem. Yeah, we'll do a bunch more of these. We're going to get a ton of written practice once I'm back live with you guys tomorrow. Let's go through 2 more of these, though, before I let you loose with the slightly harder concept builders. Okay, so one of my favorite shows is Wipeout. I'm always keen to see, that's not true, I don't watch that much Wipeout. I like The Expanse and Toradora. Those are good. Okay, anyway, dodgeball contestants. When the stuff's getting shot at them, it's interesting to see people who let it bounce off their arm versus people who catch it and drop it, or even catch it and throw it in the same direction it was going. There's more or less momentum transfer in some of these different systems. So real quick, let's set this up. How many objects are you guys reading in this word problem up here? See, I'm getting the ball and the contestant. Okay, it's 2 objects. And they appear to be separate beforehand. So I'm going to write down momentum for the first object. Oh, and we kind of get the sense that they're colliding, right? That's how you know it's a momentum problem. They're pushing off each other somehow. So there's the ball. There's the contestant. That's the total momentum beforehand. And it looks like we need to find that total. We're also going to worry later about whether they bounce or stick. Let's start plugging in some values. We got a mass of 1, moving at a speed of 15. The contestant has a mass of 75, and they were stationary. Okay, that comes out to 0, that comes out to 15. Okay, so total momentum in the system is 15 kilogram meters per second. Next step, if this is going to be inelastic, then I'm allowed to combine the 2 masses into one bigger object and have that one bigger object all going at a single speed, not 2 different speeds. So I've rewritten the right side of this equation to combine the m's with the same v. And if I do that, let's see, that was 76 kilograms of mass now. Then if I get 76v equals 15, divide both sides by 76, that gets me a velocity of approximately 0.2. Somebody with the calculator can check that later. 0.2 meters per second. Okay, so the contestant went from 0 to 0.2 meters per second by catching the ball. Let's instead solve for if the ball bounces back at the exact same speed it was inbound with. So let's go for a perfect bounce off. Okay, so I've got the inbound ball, the stationary contestant. This time though, I'm going to solve it so that it's inelastic. So I'm going to have 1 times negative 15. Now the ball has bounced off him and is heading back the opposite direction that it came in at. In the meantime, we don't really know what's happened to the contestant as a result, so that's where I'm going to put my variable. We know their mass hasn't changed, but we think that because they've been hit by a ball and it bounced off them, they might be now moving because they absorbed momentum during the bounce. Okay, so this total comes out the same still. On this side though, now we have negative 15 plus 75v. I'm going to add 30 to both sides. I'm sorry, add 15 to both sides. I'll get 30. I'm going to divide both sides by 75, and I get 0.4. Okay, so when I get back to class next Monday, we'll do some throwing and catching bricks, fun stuff. But in the meantime, what I want you guys to think about is, which is a bigger momentum change? Going from 15 to roughly 0, or going from 15 to negative 15. Which one is a bigger change on the number line? 15 to 0 or 15 to negative 15? The second one, right? So a point that we're trying to illustrate here is that elastic collisions are typically going to have higher impulse, a bigger overall momentum change than inelastic collisions. And so that's a key idea to keep in mind. And this is actually a strategy for contestants. If they can catch the ball or even catch the ball and then throw it in the same direction it was already headed, they're going to be absorbing less impulse from that collision and are less likely to get knocked off of whatever they're trying to run across. Whereas if you see them like get a nice clean bounce back off the person, that's actually double the momentum change as if they had just caught it. And they're going to get a bigger velocity change as a result and are more likely to fall off the obstacle. So kind of interesting idea there. All right, last one. This time I'm going to ask you guys to kind of think and predict. What would we do first when we read the word problem? Step 1, identify how many objects there are, and that it is a collision, which makes this kind of a momentum problem. I'm seeing 2 objects. There's a train car and there's a train engine. Were they stuck together beforehand? No. Will they be stuck together afterwards? Yes. Okay, so now I'm ready to go. I know there's 2 objects. I'm going to write down the term that represents the momentum of the car, term that represents the momentum of the engine. They're going to be separate beforehand. Afterwards, they'll be combined. By the way, if they were combined beforehand and then separated, like imagine like a firework breaking up into 2 parts. That's unrealistic. It splits up into 1,000 parts. But let's just say it broke into 2 parts for today. What would that look like math-wise? It would look like this backwards. Or like, how about a person jumping off a boat? Like, oh, well, beforehand they're connected. Afterwards, they've separated. You can flip the order of this. You can have a reverse inelastic collision to describe those kinds of examples. Or if it was separate the whole time, then both sides would look like this, where the terms are written separately instead of combining the 2 masses at the same speed. Anyway, time to plug and chug. Let's see. Train car, mass of 3,000. Velocity of 0.6. And then engine, mass of 6,000. It was stationary. Afterwards, the combined mass of both those objects is 9,000, and we really don't know how fast it's going at that point. So that multiplies out to 1,800. That's a 0. Okay, that's our total momentum in the system. That number can't change from before to after because momentum is a conserved property. You can't create or destroy momentum. It stays the same. And then what we can do is we can use that to solve for velocity after impact. So I'm going to divide both sides by 9,000. And I believe we get a velocity of 0.2. 0.2. Yeah, 0.2 meters per second. Okay. So, cool stuff. Hey, by how much did the train car slow down? from 0.6 down to 0.2, it dropped its speed by 0.4. How much did the train engine speed up? From 0 up to 0.2, it increased its speed by 0.2. Were the speed changes equal? No, it's because the masses were lopsided. The lighter object, the lower mass object, had a bigger velocity change one way, and the higher mass object had a lower velocity change the other way in order to get the momentum conservation all to work out. Okay, now, question 4. Oh, wait, sorry, question 3. We can track the momentum change of an individual object now. So I'm going to try this now. The change in momentum of the individual object depends on its change in velocity. The change in momentum, also called the impulse, would be for the train car, be 3,000 times 0.4. Where did that 0.4 come from? This was its starting speed. That was its ending speed. Ooh, you know what? Technically, I want a negative sign on that. It's dropping its speed. And what's that going to get us? Impulse for that was it dropped by 1,200. Okay, the other thing we can do for question 4 now is we can say impulse is force times time. They said that the collision took 0.1 seconds. So I can put my impulse in here. I'm trying to find the force involved. I know the time of impact was 0.1 seconds, and that means it received a force of 12,000 newtons backwards. By the way, what would be the force on the train engine on the other object? Hopefully you're thinking 12,000 newtons forward. And by the way, if the train car had its impulse of negative 1,200, it lost this much momentum, then by how much did the momentum of the train engine increase? That would be positive 1,200. Momentum doesn't just disappear. If the train car lost it, then the train engine must have gained it. It should show up somewhere else in the system. All right, and the last question on here, what's the role of the heavy-duty spring? This is a preview of a lesson coming up. The spring is designed to compress over time, and that provides that 0.1 seconds of impact, which is relatively long for an impact. That's a soft, cushy impact. That's keeping this force manageable right here. If we didn't have the spring and it was a shorter time of impact, this force would have to be bigger, and bigger forces are when things start to break. That spring is basically a safety feature to manage the impulse over time and keep the force relatively low. But that's a lesson for another day. All right, we're going to jump back now and check out the other concept builder. I feel like you guys should be good to go on this. Let's see what it's talking about. So we got 2 examples here. We got a 75 kilogram student moving at 8 meters per second in both cases A and B. And in both cases, you're going from 8 meters per second to a complete stop. So their velocity change is the same. Their mass is the same. That means the impulse is the same. So let's see, which variable is different for these 2 cases? Now, in the case of hitting the cushioning, they have a long time of impact. It's like, instead of like, so the difference in these is time. Which of these has a greater momentum change? Let's see, this one went from 8 to 0. This one went from 8 to 0 in terms of velocity. Okay, the velocity change is the same, and they're both 75 kilograms. So no, the multiple of mass times change in velocity is the same for both. And that means that they had to change their momentum by the same amount in both cases. However, in order to change momentum with a small time, you need a big force. In order to change momentum with a big time, you need a small force. So we're thinking through a couple different equations here. Let me just write those down for you to help you visualize. The change in momentum is mass times change in velocity, and also impulse is force times time. So I'm thinking through these 2 equations in order to answer this question. This was the same, this was the same, this was, if this is lower, then this must be higher, and vice versa. the cushion makes the time of impact longer, and therefore allows a decreased force. Hitting the wall directly would be over a very short time period, splat, done, all at once, which means that the force would be a lot higher. That's why it's better to run into cushions than not. All right. Let's do another one of these. I want to make sure you guys are okay with this last one here. All right. So in one of these, the catcher just holds their arm firm and the ball goes splat all of a sudden. In the other one of these, they catch it in a way that they allow their arm to come back gradually. This is like catching a water balloon or catching an egg. Whether you catch a water balloon like this or like this, you're still catching the water balloon. The water balloon is going from whatever speed it was going to 0 either way. So we're not really changing the amount of momentum we're dealing with. We're not really changing the amount of momentum we're dealing with. By the way, momentum change and impulse. Do they mean the same or different things? Momentum change and impulse. Those are synonyms. They're just trying to make sure you know that right here. Okay, momentum change and impulse means the same thing. And in both cases, we're getting a fast softball or a fast baseball, and we're catching it and bringing it to a stop either way. So that doesn't matter. What's different is the time of impact, abruptly or softly, will cause a difference in force. Force will be higher on the short time impact. I think you guys probably have a sense of that from real life. All right. Now, this one is different. This velocity goes from down to 0. This velocity goes from down to up. Okay, so negative to 0 or negative to positive, which is a bigger difference? Think about it on a number line, negative to 0 or negative to positive. When it bounces, we have a bigger change in velocity. Change in velocity, delta means the change in. With a bigger change in velocity, that means case B really does have more momentum. And momentum, change, and impulse are the same. And in order to change the momentum more, we will definitely need to push on it more. Let me bounce over to one of the trickier ones here. Okay, little water balloon, big water balloon. What's different about these is the mass. Both had the same velocity downwards and both ended up with 0 velocity later. So delta V was the same, it's the mass that's different. With a bigger mass, we do in fact have more momentum to manage, and it will take more force to accomplish that. So again, what I'm doing is I'm just evaluating this combination of ideas to get through that second concept builder. I'm just getting you familiar with the relationship with those equations. Alrighty, here are some concepts to recap. Momentum is kind of the oomph that a massive moving object has. It's relevant when it hits something else, and a collision is really just a generic physics word, or 2 or more objects pushing off each other at the same time there. It could be 3, it could be however many objects you need. We're going to stick with 2 object collisions mostly. If objects collide, then one object might be losing momentum. The other object will have to gain that momentum. The momentum can't just vanish. It has to be transferred to another object. So if you keep track of everything, which is called the system, like the system of objects, then you can track that it is a conserved property, that the total beforehand and afterwards stays the same. And that's why we're writing out that bigger equation the way we are. We're also going to categorize and think about 2 styles of collisions. Elastic ones where the objects bounce perfectly and stay separate from before to after, and inelastic where they basically perfectly stick together. There are some differences in terms of the way we handle energy, but we're not going to cover that till Unit 4. So for now, it's just stays separate. Stays separate or combines together. And when stuff is bouncing, the impulse tends to be greater because you're getting an overall bigger velocity change on that. That is a recap of all topics. If you guys then just head over, I think everything on Google Classroom should be pretty clear, which is to say you guys will be working on these 2 concept builders, and also there is a Quizlet, which you should play in match mode. See what kind of a fast time you can get as you learn unit labels, variables, definitions, etc. And yeah, I will be back tomorrow, assuming PG&E fixes power. It was supposed to be a one-day thing, so yeah. Hopefully I'll see you guys again live tomorrow, and I'll be able to answer questions. Because I'm out today, that does mean there's no hub time. So just keep that in mind, because I probably won't have internet access for the rest of the day. All right, bye everybody. Good luck on Concept Builders. Think you guys will do great.